11E is the fundamental theorem of calculus and the definite integral. We curve using an approximate method, which was the, rectangles. This section is now looking at finding the area underneath the curve to an exact degree. So it doesn't matter if it's a straight or a linear line or a quadratic line or any sort of line. We can now find the area between that line and the x-axis. We've got to be careful when we do this because we have something called the signed area. So an area that's below the x-axis is actually designated a negative signed area. We could find the area by going a half 1 times 1, which equals negative a half. So the area for A2 is negative a half. For A1, when we calculate this area, it's above the x-axis, so we're calculating a positive signed area, which we can then go, well, 3 times 3, divide it by 2, and we get 4.5. So it's positive if it's above the x-axis and negative if it's below the x-axis. We're often not interested in that negative area, and instead we make it negative so it becomes positive. But for the purpose of knowing that this exists, note that if you count it as a negative, it is a signed area. The fundamental theorem of calculus harps back to what we did at the start, where we were calculating areas underneath a curve, and we were calculating it between 2 different points. So we were making a calculation between a and b, our limits a and b, of a function f of x, and that would give us the area under the function f of x between a and b. That is what we are looking at doing here, except we're now looking at being able to do this for curves as well. So the first statement, the definite integral, is as integral between a and b of f and x. When you actually go through and solve this, you would integrate f of x like normal and get out g of x, and then you would, or you're interested in between b and a, so your limits are b and a. This notation here is perfectly acceptable and encouraged. You would then substitute in b and then substitute in a, and you'd subtract the difference. So always the top, the larger number, minus the smaller number, GB minus GA. Note that in this particular example, capital G is the antiderivative of lowercase f. Normal notation, so when you do the antiderivative, your result is a capital letter. Some properties that you need to be aware of. You can integrate something between a and b, and then for whatever reason, you can actually split that, distance or that interval. You can split that interval between a and c and b, so that in the end, you're going to go between a and b, but you're going to do a calculation that goes between c, okay? One of the reasons you might do this is because it might cross the x-axis, or there might be a point where it crosses a second curve or something like that. We'll actually deal with using this property specifically later. Another property we've got is that if your two limits, your two intervals are exactly the same, so a and a, then it's stated that there is actually no area underneath that graph. So the integral between a and a is equal to 0. If you've got a constant out the front of your f of x, then that can just be pulled straight out the front of your integral. It's a really handy property, and I really highly advise you look for it and get rid of it. This k, once it's out the front, then it just remains out the front all the way through. So there would be a k out the front of the square bracket, and then the GB minus GA would be in brackets with a k out the front of it as well. The next property says that you can actually split it. So you can split a function which is added or subtracted, so the integral of f of x plus or minus g of x can be split into an integral for f of x plus or minus an integral for g of x. So do them separately. We have already done this property, but just be aware that you can still do that. Now the last one is something we'll look at a bit more depth. This is one where what we're actually using it for, or potentially what we're using it for, is to get rid of that negative signed area. So when we're not interested in a signed area, but instead interested in the actual area, what we can do is use this property. So it says that if we're going between A and B, you can actually flip A and B. You can put B down the bottom and A at the top, which means that when I do this up here, I'm going to do G of A minus G of B. In order to do this, I do need to, I suppose, compensate for it. And the compensation that I need to do is putting a negative out the front. So negative out at the front just means that I've flipped my B and my A. Similarly, if I had a negative out the front, I could get rid of that by flipping my limits again. So it's a really powerful tool to use.